Did I make a mistake?
No, I forgot to record again, and Bernardo acted as my external memory again.
Okay.
Thank you very much, Bernardo.
Thank you. Yeah, we start with theorem C, which was at the end of the last session. Let gamma be an n module, and we are given a finite family of maximal proper n submodules. With these properties, the intersection of all the deltas is 0, and if we omit 1, then we obtain such a gamma I. We assume that this is not equal to 0, then n is a distributive sum. I explained this concept. Then n is a distributive sum of the n submodules gamma 1 up to gamma s. And these gamma 1 to gamma s are irreducible. Since we needed the context, I sent this page again. The new pages begin with 99. I give a sketch of the proof. We take one of the j's, then gamma j intersection with delta j is 0. This implies that gamma j is not contained in delta j, hence their sum is gamma. And since we have a 0 intersection between gamma j and delta j, we have a direct sum of normal subgroups. Both are normal subgroups of the additive group of gamma. And yeah, we have a direct sum, and we discussed this. We proved that in this case, both are n submodules, so we have a distributive sum, and this factor module is irreducible. Now, to take care of all the gamma j's, we prove this gamma 1 up to gamma r plus a lambda r. By induction, lambda r is an intersection of the delta I from 1 to r. That's an easy induction. And if this is true with respect to addition, then we have to show that's just application of methods which I explained, that this is a distributive sum. Now we want more decomposition theorems. As a consequence of 8.1c, we get the following proposition. Let n be a Near-ring. And we assume there exists a finite set of maximal proper right ideals with this condition, which is formed like in 8.1c. I call this combination of conditions DS, distributive sum. Then the Kj are irreducible right ideals. We have a Near-ring, and n is the distributive sum of these irreducible as of course of right submodules. This is a distributive sum of irreducible right ideals. A further proposition. Let n be a Near-ring. Now we do not take a finite set of proper maximal right ideals, but, oh, well, yes, sorry. We consider the condition that we have a finite set of proper maximal modular right ideals of n with intersection 0. We have for each of these MIs a left identity modular this right ideal. But the point of this proposition is that we can climb up to a common left identity of the whole Near-ring. Well, if S, assume S is 1, then 0 is modular, that's no problem. Let S be greater than 1. M maximal modular and K modular are assumed. We show that then the intersection is modular. Without loss of generality, we can assume that M intersection K is not equal to K, which means that K is not contained in M. Otherwise, the situation would be trivial. But M is maximal, so K plus M is N. N equals M plus K. The left, and yeah, that means that the left idea of E, this should be the left idea of modular M, and this the left idea modulo K. E has a decomposition E prime plus E double prime, and also F has a decomposition. You see, these two are supposed to be in M. These two are supposed to be in K. And F has the same decomposition. Now we do some computing with congruences. E is congruent E double prime, congruent E double prime plus F prime modulo M. Okay, look at these equations. 0 is congruent N minus En, congruent N minus E double prime plus F prime times N modulo N, because E is congruent modulo M, congruent to this expression. Similarly, we have F is congruent F prime, congruent E double prime plus F prime modulo K. And 0, congruent N minus Fn is congruent N minus F. And for F, we write E double prime plus F prime times N modulo K. And this must be true since that follows from the definition of modularity. This must be true for all in N. Hence, we have that N minus E double prime plus F prime times N is congruent 0 modulo M and modulo K, hence modulo M intersection K for all N, which means M intersection K is modular with a left identity E double prime plus F prime. Now we repeat this argument with M equals mi, k equals intersection mj, j less or equal I minus 1. And we finally obtain that the intersection of all mi, which is 0, is modular. The assumptions in the foregoing results may be derived from the assumption that we have a finite set with nice properties, finite set of substructures. What happened?
I think in the upper part of your screen, there's Near-rings charts, and maybe you should click on that.
Yes. So,
Further up.
right.
Yeah. I don't know what happened.
I think that if you go to the red icon at the bottom of your screen, the one with Acrobat Reader, and you click on it, it should show back the slides.
Yes, yeah. That's the down the red one, and in the bottom line. Yeah, this one should make it. Yeah, thank you. Gerhard, you have switched off your microphone. So in the left part of the screen, completely left, completely down, there's a button Stummschalten, and you should click on this to escape from the Stummschalten. Gerd, do you see in the last line? I think it's in the last line where it says Stummschalten. Sometimes it's also in the first line.
I think that you have to click again on the icon with the symbol of zoom. That is the blue one next to the red one. And then you will be back on the zoom. And from there, you can click the button that Günther was suggesting.
Yeah, this blue one, yeah. The blue one just left of the right button. Yeah, and one to the left. And if you click on it,
Yeah, exactly that one.
Bernardo, I just see your picture anymore, and not the others.
You can hear me?
Yes.
Okay. But I have the camera on, so you should also be able to see me.
Yes, I can hear you and I can see you, but not the others at the moment.
Maybe you fixed my face or my icon
That might.
in the Zoom, because there should be a certain point at the bottom that tells you fix this person or unfix this person. But I don't know it in German. So.
Yeah. But Gerhard Betsch still doesn't have his sound on.
Maybe if he closes the slides that he's presenting and he shares back then again, that might be an option.
That's a good idea to get out of.
Can you hear me?
Yes, yeah.
Wonderful. That was it. Somehow I activated the Stummschalten.
Yes.
Which is disastrous. So I'm very sorry. Yeah. That was the point where we started again, right?
Right.
Yeah. The assumptions in the foregoing results, they are a bit artificial, but they may derive in a very natural way from these minimal conditions. DCCR is the minimal condition for right ideals. DCC means descending chain condition, and DCCR, descending chain condition for right ideals. And one of those equations that D or A half N is 0, or one of the JNs, J nu of N is 0, nu 1 or 2. And then one has to notice that that this N plus modulo Nj is N isomorphic to Kj. Let us summarize. Let N be a non-zero Near-ring with descending chain condition on right ideals. If we have Dn equals 0, then N plus, and we can reformulate this to DCCR and this intersection. We can reformulate this to this condition ds. And we obtain N plus is a distributive sum of finitely many right ideals, which are submodules of type 0. And if we have got J nu N is equal to 0, then N plus is the distributive sum of finitely many right ideals, which are submodules of type nu 1 or 2. We may formulate a partial converse. Let N plus be a distributive sum of finitely many right ideals, which are submodules of type nu, and may N contain a left identity, so all right ideals are modular. Then Dn equals 0, Dn equals 0 if N is nu, and Jn equals 0 if N is 1 or 2. Now, We would like to have a near-ring decomposition into two ideals similar to this theorem, to the decomposition given in the theorem 8.1c. This theorem should be about the following. Let n be a near-ring, M1 up to Ms, maximal, proper, two-sided ideals with this condition ds, intersection of all the mi is 0, and the intersection over all I mi I not equal to j, call this kj, is non-zero. Then we get n is the distributive sum of the ideals kj. Of course, these kj are ideals of the ideals kj. The kj have no non-trivial ideals because, as I pointed out, we have n modulo kj is m modulo is such an intersection is kj, so that's this must be simple ideals. They have no non-trivial ideals. We could even prove more. Some of these structures have no non-zero, no non-trivial two-sided well, not ideal, how did we call it? A subnearing which is stable under multiplication for both flats. The proof is analogous to the proof of 8.1c. So what we did, we have in the not so good old days, one had to prove decomposition theorems under the assumption there is no non-trivial nilpotent ideal and things like that. And to get rid of all this rubbish, we introduced radicals, and the radicals put away with these unpleasant substructures. And now we want to capitalize on the, if we have a radical and we form the quotient structure modulo the radical, and we have that's one of the most important properties of the radical. Then we have radical free, semi-simple, or how you might like to call that. And now we want to capitalize on these assumptions. We need first this consideration. Let n be a near-ring, gamma on n modulo of type 0. That means gamma, capital gamma must be this form, have this form, small gamma times n. K, minimal right ideal of n, which is not contained in A gamma. If there is no minimal right ideal, if we have no minimal right ideal at all, then the descending chain condition doesn't hold. We didn't assume the descending chain conditions, just the existence of a minimal right ideal. And this, we assume that this is not in A gamma. If this would be in A gamma for all gamma, then it would be in A capital gamma, and so yeah, we would have a more than trivial n module. That's not an interesting case. If we have these assumptions, then we get, we did this this reasoning various times, then we have gamma n isomorphic to k. And if n is a finite distributive sum of right ideals of type 1, 2, 0, 1, 2 of yeah, this bracket is false. It should be at this place between ideals and off, right here. Then, if we have these assumptions, then any n modulo of type 1 or 2 or 1, 0, 1 or 2 is n isomorphic to some kj. That has a very important consequence. That means there are only finitely many n isomorphism classes of n modules of types 1, 2, 0, 1, and 2. The proof is easy. Now let n be one primitive satisfying the descending chain condition for right ideals. That means J, that implies that J1 is 0. Then all the n modules of type 0 are of type 1. So we have an increase of the type. And n contains only trivial ideals. What we assume means that J1n is 0, but not n. Hence, n plus is the distributive sum of finitely many right ideals of type 1. Now let gamma be a faithful n module of type 1, which means, yeah, okay. Then each distributive summand, each k which appears in that distributive sum, must satisfy gamma times kj equal to 0 for oh no, for all, yes, satisfy gamma kj, which implies gamma is n isomorphic to kj. So gamma, all the kj's are n isomorphic to gamma. They are n isomorphic among themselves. And let now let T be a 2 ideal of n, T not equal to n. Then Kj must not contained in T for at least one J. And Kj is a minimal right ideal. Hence Kj intersection T must be 0. Hence we have Kj times T is contained in Kj and T, which is 0. And all right, yes, that's that means T must be 0. Now we consider a theorem by Cully. One of the main problems in handling radical theory is, while being a homomorphic image is transitive. The homomorphic image of a homomorphic image is still the homomorphic image. But an ideal of an ideal is not an ideal in the big structure. And this problem was one of the main difficulties in abstract radical theory, and it's also quite unpleasant among the concrete, in the case of the concrete structure of a near-ring. This theorem of Cayley says let S be a two invariant subnearing of N. L be a two modular right ideal of S, which means it's a modular right ideal of S with left identity E modulo L. And let S modulo L be of type 2. Then L is a two modular N submodule. In the beginning, it was a modular right ideal of S. It's a two modular N submodule of the N modulo S, and S modulo L is of type 2. I must say we had a long discussion, Günter Pilz and I, on this proof, and I'm still not completely satisfied. I'll give the proof next time, and I'm absolutely sure that this theorem is true, but at present I cannot give a proof, a satisfactory proof, a proof which I would accept. This theorem is very important for the following. Let S be a two invariant subnearing of N. Then J2 of S is J2 of N intersection with S. In particular, I mean the similar theorem for S a ring, for N a ring, and S an ideal is true. That's one of the important theorems in the Jacobson radical theory. Here it is formulated for a two invariant subnearing of N. In particular, this holds if S is an ideal, because an S is such a two invariant subnearing. And we conclude, for instance, if S is an ideal, we have J2S is J2N intersection S. And if we take as the special ideal J2N, then we have J2 of J2N is J2N, which is in the nearing modular J2N, the zero ideal. This is a kind of idempotence if we apply this operator J2 twice. It turns out to be the same as we apply it once. Proof, let gamma be of type 2, then there exists a two modular right ideal L of S, which means S modulo L is S module of type 2. And by Cayley's theorem, we infer L is an N submodule of the N module S. Every N sub subgroup of S modulo L is an S subgroup. Well, that's trivial. No, every n subgroup of S modulo L is as an n subgroup a trivial subgroup. Hence, gamma as an n modulo is of type 2, from which we get J2S is contained in J2N intersection with S, and the converse inclusion holds since every n group of type 2 is an S group of type 2. Yeah, now a general remark. Being a homomorphic image, as I mentioned, that's transitive. Being an ideal is not transitive. And one needs special results to take care of the situation. Let us make a detour to general radical theory. We talk about the so-called Kurosh-Amitsur radicals. Kurosh was a great group theorist and algebraist in the Soviet Union. Amitsur is, I believe he was a professor in Jerusalem. We formulate the concepts first for associative rings, and afterwards you simply think of a near-ring. That's also an associative structure, but with one distributive law. A class R of associative rings is called a radical class if it's homomorphically closed. In particular, if you have a ring which is in a radical class, and any ring isomorphic to this ring is in the same class. It's also I should point out we should talk on classes, because we cannot talk on sets. This would be the whole affair would be too big. So R is homomorphically closed, and in particular, it is isomorphically closed. Every ring N contains a unique R ideal, and R ideal is an ideal which belongs to the class R. We denote it by Rn. You may call it the R radical of N, which contains all R ideals of N. You might also say it is the sum of all R ideals of N. For every N we have, and this, we have this for J2, at least for every N we have R of N mod Rn is 0. We might as well write Rn or Rn modulo Rn. Obviously, Rn defined as J2 of N defines a radical class of rings or of near-rings. Now, if R is a radical class, then SR, the class of all A, of RA is 0, is a so-called semi-simple class. We call a semi-simple class is defined as a class with the following properties. A in S, if every 0 not equal to J ideal of A has a non-zero homomorphic image in S, and if every non-zero ideal in B has a non-zero homomorphic image in S, then B is itself in S. This maybe a bit problematic. It's normally confined to sets, but S is not a set. The concepts of radical and semi-simple classes are dual. One may play with this and find out that this is true. Now a class P of rings is called hereditary if the following implication is true. If A is in P and I is an ideal. If A is in P, then an ideal is in P for all ideal in A. It's hereditary down to ideals. And to prove this, one needs a very important theorem on proved, it's called ADS, because it was proved in a joint paper by Anderson, Divinsky, and Zulinski. A radical class of associative rings, if R is a radical class of associative rings and I is an ideal in A, then we know that Li is an ideal of A. This is a this is by no means trivial. You see, we have here a theorem. If we have a ring, then R, capital R of A, is an ideal in R. And yeah, but here we have that the radical of an ideal of R is an ideal in R, not only in I. In I, this is given by the definition of the radical class. We have here that it is an ideal in A. And this has important consequences. If R is a radical class of associative rings and I is an ideal of a ring, then Ri is contained in the radical of A, contained well, I think this should be A. This should be I. I made a mistake. In particular, if Ra is 0, then Ri is 0. Every semi-simple class is hereditary. Every semi-simple class is hereditary. So being semi-simple goes down as long as you want. In order to point out differences between associative rings and various types of non-rings, one may construct semi-simple classes. Yeah, here happened a misfortune. Let's yeah, in order to point out differences between associative rings and various types of near-rings, one may construct semi-simple classes which are not hereditary. This is done in, for instance, for non-associative rings by Levitt Amentaris in a paper in the Proceedings American Mathematical Society in 1967. And in two papers, joint papers of Wiegand and myself and Cully and myself, if you take over the theory of radicals to this abstract theory of radicals to Near-rings, then if everything goes fine, you should have that every semi-simple class is hereditary. So if you can construct non-hereditary semi-simple classes, then we point out, we fix an essential difference between associative and non-associative rings, or between rings and near-rings, which are rings with only one distributive law. And this is very, 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 very strange, because it is not easy to understand why the associativity or one or two-sided distributivity is involved in the hereditariness of the semi-simple class. But obviously, we can form semi-simple classes. The general theory allows to form semi-simple classes and to form radical classes, which defines a semi-simple class, and the semi-simple class which defines a proper radical class. Nobody knows why this goes wrong with canceling one of the two, one associativity or one distributive law. I prepared, but this will be sent to you with the next charts, a proof of this ADS, famous ADS theorem, and and an indication how we can see that in the general ring case, in the case of general rings, we do have a semi-simple class, an hereditary semi-simple class as essentially different to the case of rings. Well, our next session will be the last session. I will form a summary. Even in the Near-ring case, we have other non-Jacobson radicals, the Neal radical and the radical based on prime rings. I will point out what this means and what we can do with these radicals, and then I'll give an overview of what is known on the so-called centralizer Near-rings. We have a situation that we have a group, and then we can construct Near-rings of group mappings, but we can also take homomorphisms, endomorphisms of the group and let these endomorphisms generate a Near-ring. This is a type of Near-ring called distributively generated, which have special and very interesting properties. And there is one rather remarkable result due to Fröhlich, which I will at least present. And well, then this will be this tour through Near-ring theory. Okay, let's finish here.
Well, thank you very much, Gerhard. Please don't leave the place. So the lecture next week, next Monday, will be the last one in this Near-ring course, number 2. And Gerhard Betsch offered something else. You recall that one of his lectures couldn't take place because of technical difficulties, and Gerhard Betsch will offers to give a course on or a talk on Johannes Kepler, the one who gave the University of Linz
Patron
the
saint
name.
of Linz University.
Yes, and this will be done in 2 weeks from now, at the same time, same station, which means also on Monday, starting at 1:45 Central European time, the usual time when we have our lecture. Now, it would be impossible, we agreed on that, to translate this into English, because many names of which appear there are really local names, and so it's the talk will be in German then, and I regret that the non-German
Well,
speaking.
we could. I could give a summary in German, but it's indeed difficult because some peculiar things which have to be discussed in connection with Kepler. They are very closely connected to the language, and it's okay. Well, we meet again in a week, and then if you are interested in this Kepler business but have difficulties following a German lecture, then I offer to give at least certain summaries in English.
Very good. So see you in 1 week, but Gerhard Betsch and Bernardo Rossi, please don't leave the place, because you both would like to or should talk about the exam and how it will be conducted. So I will be out of this discussion. It's up to you, and so we'll see us next week again. Thank you.
Oh,
Okay.
goodbye.